Hello and welcome to Equity Education, the chemistry version, and today we're going to be looking at buffer solutions, so buffers, and this should be following on from the acid, base and ionic products of water booklet. Okay, so I'd like you to open up your booklet and we will get going. Okay, so buffer solution. So we can describe a buffer solution as a solution that minimizes a change in pH when a small quantity of acid, H plus, or OH minus, an alkali is added. So I'll just write underneath here an acid or an alkali. You may see it written either of these two ways. Right, so we're not going to get into much detail about this, but here's two examples. So some reasons for buffer solutions include transporting oxygen in blood and the safety of many products, e.g. cosmetic products or shampoos, things like that, to make sure it's not too acidic or too alkaline with the contact with the skin. Right, so how do they work? So an acidic buffer solution can be made from a weak acid and its conjugate base, which is usually in the form of the salt of the acid. E.g., if I add ethanoic acid and mix it with sodium, we get sodium ethanoate. So an example of a buffer solution would be ethanoic acid and sodium ethanoate. Okay, so the sodium ethanoate dissociates completely because it is ionic and it produces ethanoate ion. Yep, so this is our important thing that we need to begin with. So this means that there is a large reservoir of the ethanoate ion. It also influences the dissociation of the ethanoic acid. I'll let you have a think about it, see if you can answer it. Okay, so how did you get on? Well, the reason why it happens is because if we think about it, it influences the dissociation of the ethanoic acid. So my ethanoic acid dissociates to this. So because I now have a large reservoir of sodium ethanoate ion, I have increased this concentration. So according to Le Chatelier's principle, I will shift the equilibrium to the left, which means I will increase the concentration of my ethanoic acid. So this means now that we have a large reservoir of ethanoate ions, and there is also a large reservoir of ethanoic acid, which is important for making a buffer solution. Okay, so what happens? So adding a moderate amount of H plus to the solution. So without the buffer, the pH would fall dramatically. However, due to the presence of the ethanoate ion, the following reaction would occur, which I'm sure you can guess as. So my ethanoate ions can react with H plus to produce my ethanoic acid. Okay, so this helps to maintain the pH as the equilibrium shifts to the right, removing the H plus ions. Now what does that mean? We'll go through this a bit now. So because I've added H plus here, I've increased the concentration of H+, which means I shift my equilibrium to the right. So equilibrium moves to the right. Which means for the extra H+ ions that I've added, because the equilibrium has now moved to the right, I will decrease my concentration of H+, so it will minimize the change in the H+ and therefore the pH. Okay, I hope you got that. So adding a moderate amount of H+ ions. So without the large reservoir of the ethanoic acid, the pH would increase. Why? Well, if we didn't have the ethanoic acid and hence the H+'s, there would be no H+ to react with OH-. We'll put little or no H+, because we still have some from water, and therefore we will remove most of the H+'s, so the concentration of H+ would decrease, meaning that we would have a very big increase in the pH. However, due to the presence of the ethanoic acid, what happens is that my reservoir of ethanoic acid can now react with my OH-, which will produce some more ethanoate ion and water. Okay, and this is important as well because this shifts the equilibrium to the right, meaning the lost hydrogen ions are replaced and the change in pH is minimized. Okay, so we'll just explain that a bit by drawing a diagram down here, an equation, sorry. So we're really talking about this equilibrium. So my H+ concentration here will decrease because they are being removed by the OH-, which means this equilibrium shifts to the right, which will increase my lost H+ ions, therefore minimizing the change in pH. Okay, again, hope that makes sense. Right, so another buffer solution, this time an alkaline buffer. So how do we make this? So rather than using a weak acid and its salt, we can use a weak base and its conjugate acid, usually salt, or of the weak base, or the salt of the base. So for example, we could use ammonium chloride and ammonia. So ammonium chloride dissociates in water. Plus AQ to form NH4 plus Cl minus AQ, and the ammonia in water partially dissociates. Plus OH minus. So I'll just go back up to here. So when I'm talking about this, the weak base that I'm using is the ammonia from here, and the salt of the weak base is the NH4Cl. I hope that sort of makes a bit more sense. Start confusing myself. So this means we've also got a large reservoir of ammonia and ammonium ions. So my large reservoir from ammonium ions is here. My large reservoir from ammonia is here. Yep, because it's a weak base, the equilibrium lies very far to the left, so we have a large reservoir of ammonia from here. So if I add H plus to the solution, means that my ammonia can react with the H plus to produce my ammonium ion, which also means that if I add OH minus to the solution, my ammonium ion can react with the OH minus to produce NH3 and H2O. Okay, so I hope that makes sense, and we will move on. So another example of an alkaline buffer. So an alkaline buffer can also be made from an excess of a weak acid and a strong base, e.g. so I can have my ethanoic acid, and our strong base will be sodium hydroxide. So this means we're going to have a large reservoir of ethanoic acid, and I also going to have a large reservoir of ethanoate ion. Therefore, when I add my acid, it will react with my ethanoate ion to produce my ethanoic acid. Again, this equilibrium will shift to the right, meaning that it will decrease the concentration of H plus to minimize the change, and my OH minus will react with the H plus of the acid to produce H2O, which means that my equilibrium in this reaction will shift to the left to produce more of my H plus concentration, which has been removed from my hydroxide here. Okay, hope that makes a bit of sense. I'll just go through this in a bit more detail. No, I think that's fine. Okay, so moving on. We'll now look at a natural buffer. Okay, so this comes up quite a lot in exams, in most exam boards, so we'll quickly go through it. So our blood needs to maintain a pH of between 7.35 and 7.45. To achieve this, it uses a variety of buffers. The most important one of these is the hydrogen carbonate ion buffer, which is HCO3 minus. And the equilibrium that's set up in the blood is following. Okay, so in the middle here is my carbonic acid, H2CO3, and the carbonic acid acts as unsurprisingly, an acid. My hydrogen carbonate ion, which is over here, acts as its conjugate base. So I'm assuming you can figure out what happens if we add H plus. So adding H plus, it will react with our conjugate base here to produce more of the carbonic acid. And if I add OH minus, it will react with the acid to produce H2O. And if we just go back up here, it will shift to the right from here to replace the H plus ions that are lost and therefore minimize the pH change. We'll just write that down here. Oh, wherever it's gone. So the equilibrium will shift to the right up here to minimize the loss of H plus from here, which means that our H plus concentration will not change that much. Okay, right, so I know I went through that really quickly, and there's a reason for that, and that's because these equations are written in lots of different formats depending on which exam you're looking at. I will probably do another video on how to analyze these chemical equations and explain buffers in more detail. However, I really want to move on to calculating the pH of a buffer solution. So we can calculate the pH of a buffer solution if we know the concentration of the acid and the concentration of the salt. And we assume that the concentration of the original acid is the same as the concentration of the acid in the buffer solution, and the concentration of the anion to be the same as the original salt. Okay, and again, the reasons for this is because it's negligible difference when we were talking about the assumptions to work out a weak acid. It's for the same reasons. Therefore, to calculate the pH of a buffer solution, we use the expression Ka equals the concentration of the salt over the concentration of H plus over the concentration of the acid, which means I can rearrange this to get H plus as the subject. So H plus concentration equals Ka times by the acid over the concentration of the salt. And this can be arranged to, this can now be arranged, and then we can work out the pH using minus log to H plus, or we can actually say that pH equals minus log of Ka, the concentration of the acid, over the concentration of the salt. So if I didn't want to do both of these equations, I could put them into one and we would get this. Okay, so I think this is pretty straightforward, so I'd like you to have a go at this one. So have a go at doing this worked example. Okay, so we'll just read through it. So a buffer solution was made from propanoic acid with a concentration of 0.6 mol (D(-3) and sodium propanoate, which had a concentration of 0.80. The equilibrium constant for a propanoic acid is 1.35 times 10 to the minus 5. What is the pH of the buffer solution? The equation for the equilibrium reaction is, well, technically, for right now, Ka, it would be CH, we don't do the Ca, the Ka just yet. We would have this. So I can rearrange my Ka expression to this. Now for a buffer solution, as we said before, we're going to have the salt over H plus over the concentration of the acid. So this would be my salt concentration. And I can rearrange this equation to make H plus the subject. So H plus concentration equals Ka over my concentration of acid over my concentration of salt. And now I can substitute in the data. So Ka was 1.35 times 10 to the minus 5. My acid concentration was 0.6 over my salt, which was 0.8, which gives me a value of 1.01 times 10 to the minus 5. And I can use my expression for pH to calculate my pH, which gives me a value of 4.99. Okay, so I've been through that calculation quite quickly as well, because we've done quite a lot of acids and bases calculations for the time being. I'm sure you're getting sick of them, and you've probably done a lot of them over the past couple of days or past couple of weeks. There is one more trickier buffer solution question, which is when we actually mix two solutions together to form a buffer solution. So it has a step at the start, which we haven't done. I will probably do a video on that in the future, but not just at the minute. Okay, so quick, short and simple, and I hope that was helpful, and I will see you next time. Okay, bye bye.